This is one of the monster problems in the chapter that I wanted to tackle with you. So we have a puck and another larger puck. Maybe this is on an air hockey table. So if we put glue on the edges of each of these, I shoot this puck this way and it hits just so that it attaches and sticks to the big one and they start rotating around the center of mass of the two of those. And what we want to find in this problem is we want to find out, first off, what is that angular momentum? So part A is going to be to find the angular momentum, and then part B is going to find what is the angular velocity that they have doing that. So whenever I look at finding momentum, I'm thinking through the fact that this is going to have an L equals RP equals I omega. Well, I can't use the omega because to begin with, nothing is rotating, and that looks like I'm going to be looking for the omega later, which means I'm stuck using this linear part, which is good because what I have is a linear motion with this puck moving in a straight line. So I can say that L equals RP, and if I'm talking linear, this momentum has to be mass times velocity. Well, this radius, if you remember, it's the radius that's from the pivot point. And this is where the problem becomes really a beast, because it's not the radius to the edge of the puck, it's the radius from the center of the puck to the center of mass of the system. So the first thing that I'm going to have to do in this problem is I'm going to have to find the center of mass of the system, which means that I'm stuck doing an XCM m tote. It's equal to the sum of the XM's. I can use these individually because I can treat both of these as point masses. So I'm going to say XCM m tote equals XM plus XM. Now, if I count my axis for all of this to be here in the center of this mass, then that means that that whole term becomes 0. The next thing I can do then is I can say the distance from the center of the smaller puck to the center of the bigger puck, it has to be the sum of the two radii. So this distance is going to be 0.0401 plus 0.0804, and it's the mass of the smaller puck, which is the 0.082. Now, I can divide my total mass over and just say that this is the center of mass. My total mass then will be the sum of those two masses, 0.082 plus 0.127. And when I do that, I get a center of mass of 0.047278 meters. Awesome. Now, if I draw this picture bigger, I really have this puck and this puck. And I know that this distance here is my 0.0401. I know that this total radius here is 0.0804. And I now know that my center of mass is here, and this distance is the 0.047278. So the next step then would be, eventually, I probably am going to need to know this distance. So I'm going to take the 0.0804, subtract the 0.047278, and I'm going to get a distance there of 0.033122. Now, when I'm looking at this radius, remember it's from this puck to the pivot point, the center of the small puck to the pivot point. So it's going to be the sum of these two values. So I'm going to say that this equals 0.0401 plus 0.033122. Then I'm going to times that by the mass of that small puck, 0.082, and times the linear velocity that we have, the 1.03. And when I multiply all of that together, I get an angular momentum of 0.00618, and the units for that will be kilogram meters squared per second. And there we found part A. Now, for part B, if we want to find the angular velocity, we're going to be looking at the second half of that. So we've already done a huge part of the legwork to get that, where we're going to say in part B that the angular velocity is equal to I omega. We know this L now is 0.00618. We have to find out what our I value is in order to solve for omega. Here comes the second part of the problem that's just a huge beast. So in order to find this I value, remember that that's the moment of inertia. And if I have an object that is not rotating around its own moment of inertia, but rather rotating around a different parallel axis, then I'm going to have to use the parallel axis theorem. And I'm going to have to do it for both of them because they're both rotating counter around that center of mass that is there. So I can say that my total moment of inertia is going to equal the moment of inertia of the small puck plus the moment of inertia of the big puck. So if I'm looking at the parallel axis theorem, for a disk, the normal moment of inertia is 1/2 mr squared, and then I'm going to add that to the mass times the distance from the center of mass of the puck to the center of mass of the system, or the parallel axis, the distance between the two axes. So that's going to be one of them. Then I'm going to add that to the exact same thing, but only for the other puck. 1/2 mr squared of this disk plus the mass times the distance to that center of mass between those two parallel axes. Plug in values. So if this is my small puck, I'm going to have 1/2 of the 0.082 times the radius. Now the radius from the center of mass to the center of mass, or from axis to axis, has to be this 0.0401 plus 0.033122 squared. Whoops, I messed up on that. This is what just the radius is for the spinning object. So it's only going to be that 0.0401. What I was doing was the second part of that. So I'm going to add the mass, which is 0.082, and I'm going to take it times the distance, 0.40401, plus 0.033122 squared. That's all my small puck. Now I'm going to also add the big puck. So I'm going to have the mass, which is 0.127, times the radius of the big puck, which is 0.0804 squared, plus the mass of the big puck, 0.127, times the distance between the two axes, the center of mass of the system and the center of mass of the small puck, which is that 0.047278 squared. So that's all the big puck. And when you punch all those values in, you're going to get a moment of inertia of 0.00120 kilogram meters squared. Biggest part down now. Now we have our I value, 0.00120. We can solve for omega. Omega will equal 5.15 radians per second. And that will be our answer to part B. So the tricky part in this one has really nothing to do with finding this moment of inertia and finding the omega value. It's really all of the center of mass and the parallel axis theorem involved in the moment of inertia, and that's what makes this a really good AP problem, because we're dealing with a whole bunch of different topics all embedded into one problem.